Hi, I'm Mohammad, and I would like to briefly talk about our recent work, which is about evaluating neural encoding models using information gain. I will talk about the challenges we faced while doing this and how we try to address some of the challenges in this work. But before we get into that, let's talk a little bit about why does this matter. In computational neuroscience, there are several normative theories that link neural variability to cognition. These theories not only make predictions about the mean firing rate of neurons, but also about higher moments of their response distribution, or even the full distribution as a whole. Examples of such theories are probabilistic population code or neural sampling hypothesis, where both theories, one way or another, involve statements about the distribution of neural responses. So it is quite important to quantify how well encoding models account for the full response distribution. But the metric that is most commonly used these days to evaluate and compare neural system identification models is correlation, which is only sensitive to the mean, and therefore it is not really suitable to measure performance of the models that capture the full distribution. A suitable metric that could be used for such a purpose is information gain, which was introduced amongst others by Kummer et al. In 2015. Information gain measures the likelihood of the model, which is shown in blue, relative to a lower and upper bound estimator, which we refer to as the null and gold standard model. This way, we can evaluate encoding models by how well they capture the full response distribution, and importantly, it is interpretable since the performance is put on a scale between 0 and 1. However, while computing this, it turned out that it is not so easy to come up with a good gold standard model, and this is what our work is mainly focused on. So let's talk about how we can compute this gold standard model. Given repeated trials, the naive approach to obtain a gold standard model is to estimate the distribution parameters as point estimates by moment matching. But since neural responses are usually very sparse and datasets are small in size, this approach heavily overfits. You can see this in the figure where many neurons are in the red part, where the null model has a higher likelihood than the gold standard model. To address this problem, we propose a Bayesian approach for computing the gold standard model using the full posterior predictive distribution. This essentially means that instead of having point estimates, we add uncertainty to the estimated parameters. This approach addresses the issue of overfitting, and we get a reasonable gold standard model where almost all neurons, shown in orange, are in the green part. We also provide full mathematical derivations of the posterior predictive for the state-of-the-art zero-inflated distribution models, which you can find in the paper. We then tested our Bayesian gold standard model and compared it to the point estimate approach. We found that our model outperforms the point estimate, especially on the higher moments of the distribution, which is what we wanted in order to evaluate the full response distribution. We also found that the Bayesian gold standard is more robust to different signal-to-noise ratios, and also it is more data efficient than the point estimate. This is especially important when working with neural data, which is difficult to obtain in real experiments. Finally, we applied this metric on models that are trained to predict neural responses. Specifically, we trained a zero-inflated log normal distribution to the responses recorded from mouse primary visual cortex to natural images. On the left, you see model performance based on log likelihood normalized by the performance of the gold standard model, where the null model is shown in red, the trained model in blue, and the gold standard in yellow. The bars with gray color are model performance when we match different distribution parameters of the trained model to the gold standard model. While matching different parameters resulted in some improvements in the trained model, in general, the trained model has captured all parameters similarly well. And on the right side, we have the same result, but relative to the null and gold standard model, which shows that the performance of the trained model is at 90% of the maximum achievable performance. All right, that was all for this brief description. And if you're interested in more details and want to know more about this project, do come to our poster or check out the paper. Thank you.